All right. So I hope that this audio is visible to, sorry, video is visible to everyone. Okay. So we were discussing about these kind of cases. These are very, very simple cases. First, you have to get this in your mind. Everything is easy. Everything is easy. Everything is easy. All right. Okay. And now let's just check one by one. Fine. We'll be proving the results over here. All of these cases over here, right? These, this one, and this one. Very simple there. You don't have to do anything actually. So how do you not do anything? Fine. Okay. So we'll just write whenever you have, can you notice that these systems have common magnitude of acceleration? All of these systems, they have common magnitude of acceleration, right? This one will go up by a, this one comes down by a, this one will go down by a. This one has an angular acceleration of some alpha value. This one will have angular acceleration alpha value. This one will be going up by a. This one has alpha value angular. This one will have probably another alpha value of acceleration and so on. This one is going to go down by a. So all of them have same magnitude of linear acceleration, right? We say that is true. All of them, when we say the blocks. So in all such cases, what you can write, all of these cases, the common magnitude of the acceleration, this way you can directly write A as equal to the net force which is trying to pull the system. Net pulling force, not the pushing force. Net pulling force. Okay. Divided by the equivalent mass of the system. And when we say the equivalent mass, you'll have to write the sum of all the translational masses plus the sum of all I by r square terms. Dimensionally, this is what it mass. And in the proof, it comes out to be this way. Where can you apply this? Only when you have the pulley cases. You have multiple pulleys, and all of them have just angular acceleration, and the string which goes around is connected to blocks. There is only one magnet. It's not that differing acceleration values are there. In that case, you directly apply it. For example, the first one. In the first case, what is the force because of which these blocks are going to accelerate? The weight, right? Over here, these two forces, M2G and M1G, these are actually opposing forces. Can we say that is true? Definitely. Definitely. So if this is true, then what is the net force which is trying to make the system accelerate? Can we say it's the difference between these two, M1G, M2G and M1G? Yes, that's the net pulling force. What about in this case? What is the net pulling force, do you feel? Can we say it's just mg, which is trying to make the system accelerate? Yes. What about in this case, the third one? Over here, again, m2g, and this one is m1g. So again, it's the difference of the mg forces. That's the net pulling. So therefore, for the A case, the common acceleration, you can now write it as equal to much. Oh, so it goes like this. Right. So therefore, now you can write that in the A case, this acceleration is m2g minus of m1g divided by the equivalent mass of the system, which is the translational mass, which is m1 plus m2, plus I by simply r square radius of that pulley. Now we're coming to the proof of this. And proofs are definitely essential because the human mind is very rational, right? It demands proof. How, right? So let's get into that. So how many objects are there? Two blocks and one pulley, right? So we'll write the Newton's law on these three. F net equal to ma for first block, F net equal to ma for second block, torque equal to I alpha for the pulley. We'll also write one constraint for the pulley, because there is some relation between the angular acceleration and the linear acceleration, right? One more constraint is required. So on the block called M2, what are the forces? This is your M2G, and this is the tension force. Let's call that T2. Okay. T2 is that what force? The tension force, right? Fine. And similarly, on the right side, what do you have? On the right side, this one is M1G, and what do you have? Tension force T upwards. And we said that M2 is greater, right? So acceleration this way, this one acceleration this way, fine. Pulley. And on the both the sides of the pulley, there will be the force of tensions, right? So over here, in this part of the string, there will be a force called T2. Okay. Why? Because it's connected to this particular block over here, right? So therefore, this is nothing but the force of T2. And similarly over here, you would be having the force of how much? T1, right? Why? Because you have the other one connected over here, right? T1 is connected this way. Fine. And now let's write the what law? Newton's law. On what? On the mass called the M2, F net, which is M2G minus T2 is equal to how much? M2 times of equation number 1. And on the mass called the M1 mass, what do you have? T1 minus M1G is equal to M1A. Fine. Equation number 2. Notice how many unknowns are there. T1, T2, and A, 3 unknowns. And now let's go to the pulley. So on the pulley, what do you have? What do you have on the pulley? Right? So on the pulley, uh, again, what is the direction of the angular acceleration? If the left one is going to go down, can we argue that this will be the direction of alpha? Yes. So this is the direction of alpha. Then the net torque is nothing but equal to how much? Moment of inertia times the angular acceleration, alpha. Torque is I alpha. Fine. So therefore now let us write that this is nothing but T2 multiplied by the radius minus T1 multiplied by the radius. Why? The torque due to T2 will be positive because it is in the sense of alpha, whereas the torque due to T1 is in the opposite direction of alpha, so it's negative torque. The perpendicular distance over here is nothing but the radius, and sine theta is sine 90 itself. Fine. All right, so therefore this becomes equal to how much? Moment of inertia times alpha. This becomes equation number 3. Now, how many equations are there and how many unknowns are there? 3 equations, and unknowns are T1, T2, A, and alpha. Masses and radius are known to us. Moment of inertia also known. So 4 unknowns and 3 equations. How do you solve? You can't solve actually. No one can solve. So what we do is we actually need one more equation. And wait a minute.